7b, confidence intervals for a population mean where we have a small sample and the population standard deviation is unknown. Now previously we talked about where you had a large sample or the population standard deviation was known. And we could use that method if either one of those things was true. If we knew the population standard deviation, we could use that method. If we had a large sample, we could use that method. We didn't have to have both of them occur, we just needed one or the other to occur. If they both occurred, great. But we only needed one of them to occur. Now we're going to look at, well, what if we don't have a large sample and we don't know the population standard deviation? Well, the process is going to be very much similar. In fact, it's going to be almost the same, the only difference being that we're going to switch to a different table. So now, instead of dealing with a z distribution, which is what we were dealing with before, the standard normal cumulative probability, we're going to deal with the t distribution. So the t distribution, and that's sometimes referred to as the student's t distribution. Okay? So the only change to things is we're going to change our variable names just a little bit. Now instead of having z sub c, we're going to have t sub c as our critical value. Instead of having a margin of error that's equal to z sub c times sigma over the square root of n, we're going to have a margin of error that's equal to t sub c times s over the square root of n. Why s? Because we don't know the population standard deviation. So sigma is unknown, so we're always going to use s. Because it's a small sample, we don't know the population standard deviation, then we're going to be using the t distribution, so our critical value is going to come off of this new table. Otherwise, everything else is going to work the same as it did for a large sample or if we knew the population standard deviation. We're still going to take the point estimate x bar and we're going to add and subtract the margin of error, and we're going to find our confidence interval. So let me introduce you to this new table. So this new table, I know you can't see it well here, but it is in the tables folder. So critical values for the student t distribution. Like I said, I know you can't read it, but I can try the best I can, right? Now there's a couple things I need to note with this table. First of all, if you look in the upper right hand corner of this table, you'll see that it shades in the upper right hand tail. So the upper tail. Whereas with the normal distribution, it dealt with the lower or the left hand tail. So that's one thing to take note of. You'll also notice that it has degrees of freedom. I'm just going to put that as df because you'll see degrees of freedom and then it'll say df. So you have your degrees of freedom, 1, 2, 3, continuing down there. And then you have the upper tail probability. So your upper tail probability. It has things like 0.40, 0.25, 0.10, 0.025, etc., etc., 0.01. So it has those. So upper tail probability, remember when we did the thing, we said, hey, if we've got a 90% confidence interval, then we have 10% left over in the tails. We've got 5% here and 5% here. And we said that 5% was 0.0500. So we'll say 0.05 in that upper tail. So now we can look at the top of this and we look for the column that has 0.05 in the upper tail. So that's the one part. The other part of it is this degrees of freedom thing. What is this degrees of freedom? Degrees of freedom is equal to n minus 1. So it's one less than our sample size. That's what degrees of freedom is, one less than our sample size. But what does that really mean? Well, let's think of it this way. Let's say I have a classroom with 20 chairs in it, and I have 20 people coming into the classroom. If they come in one at a time, the first person that comes in has 20 choices of where to sit, which chair to sit in. The second person has 19 choices. The next person, 18 choices. The next person, 17 choices. It kind of sounds like when we were dealing with counting and probabilities, right? So we go through that. Well, once 18 people have entered the room, I have 2 people left and 2 chairs left. So that 19th person walks in the room, they have a choice of 2 places to sit. When the 20th person walks in the room, there's 1 seat left. That person no longer has a choice of where to sit. They're stuck with the remaining seat. So out of those 20 people walking into the room, 20 minus 1, or 19 of them, had the freedom to choose their seat. The last one did not have the freedom to choose their seat. Therefore, with a sample size of 20, the degrees of freedom are 19. 19 out of 20 of them had the choice. So degrees of freedom is just the sample size minus 1. So when we want to find a probability, a critical value T sub c, we're going to use the upper tail probability across the top, and we're going to use degrees of freedom going down the side, and that's just n minus 1. Other than that, it's all going to work the same. Now, I'm going to let you in early on this little secret too. If you look at the bottom of the table, then you'll see that it says confidence level C. Confidence level C. And we'll see that it actually gives us percentages for the confidence levels. So 4.40 has 20%, 0.25, 50%, 0.10, 80%, 0.05, we don't have here, 0.025, 95%. Right? So each of these upper tail probabilities, there's an associated confidence level. So what we can do is, just like with the normal distribution, we had that little table in the bottom left-hand corner. For the t-distribution, we can look down at the bottom and say, okay, we're looking for this confidence level, and then go up to our degrees of freedom. So let's give this a shot and see how it works. As you see, it didn't really change much. We need to find degrees of freedom, and our formula changed just to be T sub c instead of Z sub c. So I'm going to get this out of the way here. And I'm going to put margin of error equal to T sub c times S over the square root of n, just so we have it there as a reminder of what we're doing. We want to find the average time that it takes a student to complete an online stats exam. And we want to find that at a 98% confidence level. So we're looking for population mean average time. We take a sample of 13 students and find the average amount of time to be 56.4 minutes with a standard deviation of 7.2 minutes. And we want to find the 98% confidence interval for the population mean. Now note here, the sample size is 13. We have a small sample. It's less than 30. And we only have the sample standard deviation. We don't know the population standard deviation. Therefore, we have a small sample and the population standard deviation is unknown. So therefore, we're required to use the t-distribution. So right there, that tells me t-distribution. Okay, so if I'm going to use the t-distribution, I'm going to need degrees of freedom. Degrees of freedom is equal to the sample size, 13, minus 1. So we have 12 degrees of freedom. We're dealing with a 98% confidence level. So I'm going to look at the bottom of the table. In this table, it's just above where it says level C. We see 98%, and then I go up to 12 degrees of freedom. And I see 2.681. 2.681. T sub C, our critical value. So I looked at the bottom of the table to find my confidence level, and then I went up to the proper degrees of freedom, which was 12, and I got 2.681. So now that I have that, I have everything I need to find my margin of error. So my margin of error is equal to T sub C, 2.681. We're going to multiply that by the standard deviation, 7.2, divided by the square root of the sample size. Remember, the sample size was 13. Our degrees of freedom was 12, but our sample size is still 13. So we're going to calculate that, so grab the calculator. At 2.681 times 7.2 divided by the square root of 13 gives me 5.35. So my margin of error is 5.35. So now that I have that, I can find my confidence interval. Point estimate, 56.4, minus our margin of error, 5.35, and 56.4 plus 5.35. So 56.4 plus minus 5.35 gives me 51.05. I'm just going to make that parenthesis a little bit bigger there. There we go. And then 56.4 plus 5.35 is 61.75. And then as before, the final step is we need to write down what this is. This is a 98% confidence interval for mu. We're 98% confident that the average amount of time that it takes a student to take an online statistics exam is between 51.05 and 61.75 minutes. And that's our process. Very similar to the process that we did previously. We have to look and we have to determine, do we have the population standard deviation? The only way we can have that is if we're told we have the population standard deviation. If we don't have the population standard deviation, do we have a large sample? If we have the population standard deviation or we have a large sample, we go back to using the z distribution. But if we don't know the population standard deviation, we don't have a large sample, then we're going to go to the t-distribution. So now that we do that, we need to find degrees of freedom. We use degrees of freedom and our confidence level to look it up in the table to find out our critical value, T sub C. Then we plug that into the formula, T sub C times S over the square root of n, giving us a margin of error, and subtract that from the point estimate, the sample mean, and then label it as a such and such confidence interval for mu, the population mean. You've got to put all these things in there. You have to tell me what percentage it is for the confidence level. You have to tell me that it's for the population mean. If you leave that out, or if you leave that out, then you didn't do it properly. You've got to give me all that information. Without it, we don't know what this interval is talking about. So remember, when determining what distribution to use, first thing you look for is the population standard deviation. It has to be stated, population standard deviation. If that's not anywhere to be found, then we look at the sample size. If we have a large sample, we can still use the z distribution. But if we don't have a population standard deviation and we have a small sample, that's when we come to t. And if you look at the table for the t distribution, you will see that at the very bottom is z. And z is always a smaller number than any of the associated t-scores on there. So any of the values, if you look at any of those columns, the numbers start larger and they get smaller as they go down. So if our critical value t sub c is always greater than z sub c, our critical value for a normal distribution, obviously we're going to get a nicer or smaller confidence interval if we can use the z-score, the critical value z sub c. So if we have the population standard deviation or we have a large sample, we want to use the z distribution to do that. But otherwise, that is the process. Now we never find the minimum sample size necessary to get a certain confidence level using the t distribution. So we don't have a reversed formula n is equal to such and such. If we're trying to determine the minimum sample size necessary, we always use the z distribution for that. So there is no equivalent with the confidence interval for a population mean of a small sample where the population standard deviation is unknown.